Okay. Um, so I mentioned on Friday what the format will be for the final. So I'm working on updating the practice final, and I'll have it up certainly by Wednesday, if not sooner. So the practice problems that are already there, that part's going to stay the same, and because what I intended before was having 15 or so problems spanning the whole course, regular problems. But you have a question? Oh, you're just stretching. Okay, all right, good to know. That instead are going to be eight regular problems that are all from the new material, higher order equations that I covered last week, and then Laplace transforms that'll start in a few minutes. And the other part will be this lightning round I mentioned. There are questions similar to reading questions. And in fact, studying the reading questions that you've had is a great idea. Hint, hint. No, they will not be the same questions. Okay, so you'll be fine. so, and the idea is I'll probably choose put 15 questions on there, but say you need to answer 10 of them, or you can answer as many as you like, and I'll count your best 10 in case you want to. You're not sure about some of your answers. So it'll be something like that's roughly half, and then the other part is roughly half. And then what I will do on the last day of class, so Friday, May 5th. So instead of doing what we did before, a test where you have a test for 50 minutes and then you come back and have another half hour to work on it, now it's kind of reversed, where I'll give you some problems, a portion of a final here in class on that Friday. So we want to have better attendance in this, just FYI. I mean, you'll all be fine, but everybody else needs to show up. By the way, I checked. I figure, when people don't show up, and we've had on average 10 or so people not show up each day lately. Okay, oh well, all right, that hurts their attendance grade a little bit, but at least they can watch the video. They're not watching a video either. I can check how many views there are. There are not many. So, of course, the people who need to hear this probably are not here and won't see the video of this either. So, okay. So expect an angry email to the class. Now, so on that Friday is where we start. So I will take just a portion of the test, and so you can work on that, and then you'll turn that in, and then I will give you on Wednesday, May 10th. This is during finals week, and we're the early slot. I'm not happy about it either. I'm not the morning person I used to be. Is where everything comes to an end. So what I will do, and this is going to be kind of a pain paperwork-wise, but I'll give you back what you worked on the Friday, with not corrections, but pointing out where you went wrong, like I did before. So then you can continue that, and you'll also have the rest of the problems. And on the practice final that's up there now, there is a rather extensive formula sheet. So you'll have that. So the only thing that you haven't seen yet is what are these reading question-like things that I'll be putting in there. But within a day or two, you'll know. And in addition to studying prior reading questions, I'll just tell you up front. I'm going to think of some questions off the top of my head, like I've already been doing. And if I have trouble thinking of more off the top of my head, then I'm just going to look at my own notes, which you have access to. So that's a really good place to look for the kind of things that can be asked. Okay, so any questions about what to expect with a yes?
On that Friday, it's just going to be problems that we get, not the reading type.
Right. Yeah. Only regular problems and yeah.
So we're only going to have 8 problems on the new stuff, basically.
Right. But the reading questions or lightning round covers the whole course. That part is comprehensive.
We don't have to work any.
Right. Although I should mention that some of the things that you use for result problems naturally come up. Like part of it's going to be higher order equations, like last week, which involves all the same things you did for second order equations. So it's not. I wouldn't call it intentionally comprehensive, but naturally comprehensive. The lightning round is intentionally comprehensive. I just made those terms up, but I think you get the idea. Other questions? Okay. What's been interesting is I haven't always given this format, but some students seem to just do exceptionally well on the lightning round part and really boost their grade doing that, which is not something I would normally expect. Okay. But the whole idea is to make sure that that you all understand what goes into these processes, where they come from, why we use this approach for this problem, etc. The essential properties of these methods, because that's going to be just as relevant as techniques themselves if you should ever have to use these things in some of our class. And yes, believe it or not, it actually does happen. Okay. Well, there are two courses that are sequels, if you will, of this one. There's 415 that's offered every fall. That's required for physics students. That's continues of ODEs in a mathematical physics sort of way. And then in every spring, there's 417, partial differential equations, which is where I do my research on, and it gives introduction to that topic. Usually it's either Dr. Zhu or Dr. Chen who teaches those classes. I've taught them before, but I'm like, not again. Well, I mean, they're not that bad, but there are other courses that I enjoy teaching more. Like 460. I'll look forward to seeing some of you there. Also, I just want to mention, so last Saturday, this past Saturday was the annual undergraduate symposium on research and creative activity. Even though this university has a lot of budget problems that I'm sure you've heard about on some level, thanks to some wealthy alumni, very generous, wealthy alumni, undergraduate research is something they really support. So actually, one of my own honor students just took first prize, so I had to brag about that, Sarah Long. And then also, because they have the Spur Awards, the Eagle Scholars Program, every semester. And I've had a couple students win things there. There's also, in this department, we have Dr. Xi, who we just hired, which is his first year here. So he administers the Cross Scholar Program, so we put out scholarships every year. So he runs a process, and some students work with him directly, but it's to work with whoever. I did undergraduate research during 3 of my 4 years as an undergrad. When undergrad research wasn't really so much a thing way back then, but it's a great experience to add to what you see in classes. And just on the purely superficial side of things, there's money in it for you. So, well, I was adding it up, between undergraduate and graduate students, I've never been able to get funding for myself since I've been here. That's the one thing I've not been able to accomplish. But my undergrad and graduate students have raked in about, I think, like $70,000 or so across several awards during the last 5 years. So I can't get money, but at least they can. Okay. Now, final part of the course. Laplace transforms. Not Laplace. If you pronounce it that way, you're flunking. What? Yeah, that's a good bet. Although another very famous French mathematician, and actually I think they knew each other, Fourier, because there are many other transforms. There's Fourier transforms, which if you take either of those other classes I mentioned, you'll find out about. And that would explain how to pronounce that, but then some students heard how it's pronounced from me, but they didn't know how it was spelled, then they spell it phonetically, and whoops. Now, the idea behind transforms such as the Laplace transform And this is a great subject for a reading question, I might add. It's what kind of transformation does it achieve? It changes a differential equation, like the ones we've been solving, into an algebraic equation. Okay. Of course, if a student from Math Zone heard that, they'd probably think, well, why are you making it harder? Okay. Or that might apply to some of y'all. It seems that no matter what the class is, algebra ends up being a problem. But anyway, conceptually, this should make the equation a whole lot easier to solve. And that's why we have it. Also, another virtue of Laplace transforms makes it the process of solving a differential equation by Laplace transform makes it easier to take the initial conditions into account. Whatever initial values you're given, like for y of 0, y prime of 0, you can just put them directly into your Laplace transform formulas that you'll see a little later. And you don't have to solve for a C1 and C2. Again, that's not a difficult process, but it's a process where that invites mistakes. I've seen quite a few of them. So that part of the process is nicer. Okay. Now, before I explain what is a Laplace transform, I need to introduce some notation that I'm going to use the whole time. Because we're going to cover this all this week, and then again on Monday we finish up. Wednesday's review, and then that's what happens on Friday. Okay, so the idea is you have your differential equation where you're solving for y of t, as always. And what you do is you take the Laplace transform of everything that's in your equation. Y prime, y double prime. And the notation that's used to describe a Laplace transform is this fancy L, and you indicate this is what you're transforming, in this case y of t, that's put in curly braces. This is the kind of notation that the textbook uses also. And the output so the input to the Laplace transform is a function y of t. The output of the Laplace transform is another function, but of a different variable. And the way it's depicted in the textbook and in my notes is an uppercase y, and with a new variable s. So you can think of the original function y of t as being what is called physical space, because you're dealing with quantities from reality, like space and time. Whereas s is referred to as so now we're in what's called frequency space. So s is your variable in that space instead of t. So in other words, t is out of the picture. Now you only have functions of s.
Is that an L?
This is, yes. But it's a fancy script L, like you can see in my notes or the book. All right. Now, as you can see on the board, even though it's pretty easy to distinguish in my notes or in the textbook, it might not be so easy to distinguish on the board. So I'm going to write this uppercase y a little differently, like that, so to distinguish from plain old y over here. Okay. So what happens is you give a differential equation like a kind you've always seen. Take the transform of it to get a new equation that's an algebraic equation for a function uppercase y of s. Actually, I'm going to, what's also used to indicate transforms, notation-wise, more often with other kinds of transforms, but a hat. So I could use either one here on the board, but preference? Hat or? Let's go with a hat. Okay. All right. Just keep in mind there's no hat in the notes, but it's obvious in the notes it'll be uppercase. Okay. And then what you do is you go ahead and solve an algebraic equation to get the transform of your solution. But what you want is your y of t. So you have to go back. So you have what's called an inverse Laplace transform. So this is a two-way process. And you get same fancy L. But now with an inverse to get y of t. All right. So transform, solve algebraic equation, transform back. All right. Now, 1 second, I'm going to go for help and grab my textbook. I'll show you something in it. And yes, I know normally don't make use of textbook at all, but that's weird. Okay, I want to call your attention to one page in it. Oh, by the way, one thing I discovered a few weeks ago was, remember when I was away and Dr. Tian substituted and covered the section that I'd just been covering. And it turns out, here's the reason why. Depending on how you acquire this textbook, like if I looked, I was at home, I didn't have this with me, so I went to download a PDF. And 10th edition, I checked to make sure it's the same edition. But it's different. So the section that I asked her to cover 3.3, she did in that edition. So I don't know if it's an international edition or something, but different 10th editions are different, which is kind of troublesome. So now I know why that happened. Okay. So in this version of a textbook, which hopefully is what you have, whether you bought it or downloaded it or whatever, is, show everybody here. Okay. Table of Laplace transforms. All kind of transforms like this have tables that you can either find in a textbook or you can look up online. If you just Google Laplace transform table, you'll find one. So what will happen is, so you'll be referring to this page often when you're doing homework on this chapter, and during a final, I will make photocopies of it and distribute them, so you'll have that in front of you. Okay. So what you can do now is give the definition of a Laplace transform and show you some of the basic rules, and then we'll get into how you can actually use them to solve the kind of equations that you're familiar with. This. Okay. Okay. So Laplace transform of a function, any function, f of t, which I'll refer to using the same notation as over there, f hat of s is defined as an integral that has a parameter in it. So it's the integral from 0 to infinity e to the minus st f of t. Okay. So everything we're doing with Laplace transforms, all the rules that are in that table, for instance, come from this definition. Chances are, though, you will never actually be using this definition. So I have some examples in the notes of how the definition can be used to derive certain rules. Generally, you just be using those rules directly. But just to give you an idea of how these things work, because what happens is you're integrating with respect to t, but it's a definite integral in t. So that's why the result of this is not going to have t in it. But you can think of s, from a point of view of the integral, s is like a constant. But it's left as a variable. There's no value substituted in for it yet. So that's why what you get out of this happens to be a function of s. Now we deal with improper integrals, so you have to take a limit as t goes to infinity, etc. But we're working with functions for which that can be worked out. So a few examples. Let's let f of t be equal to 1. So its transform is just going to be the integral of e to the minus st times 1. What is that integral? Just the antiderivative.
Negative e to the st.
Negative s. E
Oh,
to the negative s.
negative 1 over s.
Yeah, you divide by the coefficient of t, which is minus s. Okay, and then you have limits 0 and infinity. And we're assuming that the parameter s is positive, so its exponent is going to be positive no matter what. So what happens when you plug in the limits?
You get negative 1 over s.
What?
You get by s.
Yeah, so you get 0 when you plug in the upper limit of infinity, minus, and then e to the 0 is 1. Yeah, so 1 over s.
How'd you get 0?
Basically e to the minus infinity is 0. Because, and some of my colleagues will shoot me for running this, but it works.
Okay, I was just,
Yeah.
that helps, I forgot that news thing.
Okay. All right. So another way of writing this is the Laplace transform of 1 is equal to 1 over s. Okay. Now, similarly, this would require integration by parts. The details are in the notes. Laplace transform of t, so if f of t equals t, you get something similar. It's 1 over s squared. And what you can do is keep going. So in general, Laplace transform of any power of t is, so t to the n is n factorial, and then you have s to the n plus 1 in the denominator. So notice, whatever power of t you have that power plus 1 in the denominator for s, and here you might, from these two, you might think, oh, the numerator is always 1, but no, it's not. It's whatever power you had, that factorial. That's what goes up here. It's just that 0 factorial and 1 factorial were both 1, so you couldn't really tell that. So this is one very important rule, and it's one of those that's in that table, how to transform powers of t.
Where did you get the second part from? The Laplace?
This one?
Yeah.
I didn't actually work it out here because what I would have to do is integrate t e to the minus st, and that would require integration by parts. Now, if you look at page 86 in the notes, that integral is completely worked out there. Well, I want to spend my time here dealing with how we actually use this to solve differential equations. In other words, the sort of things you'd actually be doing on a test. But there is, well, there are a couple more though. Of particular interest. Okay. So another example would be, this one is not hard to work out as far as the integral is concerned. E to the at. Now this is of interest because we see this in all the time in the equations that we solve. So f hat of s, which is the Laplace transform, Laplace transform of e to the at. So we apply the definition. So we have e to the s minus st, and then our function is e to the at, so we'll put that in there. But now what we can do is combine these into one exponential. So e to the minus, and then we have s minus a t dt. So now you can work out this integral essentially the same way as the other one. You're dividing by the coefficient of t, but instead of being minus s, it's minus s minus a.
Why is it minus A and not plus A?
Pulled out the minus. Because if I distribute this, then I get minus minus a, which is a plus a. With limits 0 to infinity, and then when you plug in the limits, you plug in infinity, you're going to get 0 again. And then when you plug in t equals 0, this becomes 1, and you're left with 1 over s minus a. So notice the Laplace transform of 1 was just 1 over s. But then when you have an exponential, that causes a shift. Now, and I'll ask you to recall something from algebra that we haven't touched here, but if you think of 1 over s as opposed to 1 over s minus a, how do you get the graph of this from a graph of the other? What graph transformation is that? Does anyone remember?
Horizontally, shift to the right with F.
Yes, a shift to the right by a units. Okay. All right. So, and in fact, in general, when you're transforming some function and you multiply that function by an exponential, that causes a shift in the Laplace transform to the right by this many units, however, whatever constant you have here. Now, one in particular that's helpful for differential equations is what if you have a derivative? So let's suppose you already know how to transform f of t, but now you want to know how to transform its derivative. Can you express the transform of a derivative in terms of a transform of the original? The nice thing is, yes, you can. That's what really makes this technique helpful. So that'll be the integral of e to minus st. Now you put f prime of t in here. And now what you do is, and the idea is you're using the fact that Laplace transform of f of t is already known. So we want to express our answer in terms of this. So what we can do is use integration by parts. This is the dv, and that is the u. So what you get is u times v, and the v would be f of t, with limits 0 to infinity, minus integral of v, which is f of t, and then we have du, but that's going to be minus s e to the minus st. So this is your du, and that is your v. So integration by parts by itself gives you that. Now, you go ahead and plug in limits. When you plug in infinity here, you're going to get 0 again. And then when you plug in 0, you're going to get 1 here, and then f of 0, whatever that might be. And with a minus, because it's the lower limit. So that's all that comes out of this part. And now I'm going to factor out this minus that's going to pull it out of the integral. And the minus gives you a plus s. And if you look at what's left, 0 to infinity e to the minus st f of t. Now, if we focus just on this integral, now f is an arbitrary function, so we can't actually work out the integral. But what does this in the box represent? How can we refer to that? Look at where we've seen it before. Yeah, it's a Laplace transform. This is exactly this. So it concludes that the Laplace transform of f prime is s times the Laplace transform of f, and then you subtract off f of 0.
So we're using the same thing that we're gonna end up finding. You said we're using it up there.
Yeah, so the point is, once you know how to Laplace transform a function, you know how to transform its derivative. It just builds on top of that in a very simple way. And I'll show you in a little bit how I'm going to use that to, whoops, sorry to those not enough people who are watching, how to use this to make differential equations easier to solve. Now, this is a rule for transforming first derivatives, but we're interested in second order equations too. So if I wanted to plus transform of f double prime, I won't carry out here, but it would be the similar approach. You'd have f double prime here. You have to apply integration by parts twice. And that's going to result in s squared. And then you have two terms to subtract off. So minus f prime of 0, and then minus s f of 0. So if you were to carry out the same approach, integration by parts, but twice, so the first time around, like right here, we give you f prime of 0. The second time, we give you this one. Okay. So now, okay. So now we have what we need to take the transform of a second order initial value problem, like when we were solving back in chapter 3. So instead of doing characteristic equation and all that, we can use this and get an algebraic equation to solve. So I'll go through an example of that. And if there's any other rules, they're all in that table, but I'll introduce them along the way. Okay. What I have in my notes is general. I'm just going to make up some numbers here. Okay. So y double prime plus, let's say, minus 5y prime plus 6y equals 0. And then I'll make up some initial conditions. Okay. So what you do is you take a Laplace transform of the entire equation, because we have rules for transforming y double prime and y prime. So the Laplace transform of y double prime is written over there. So it would be s squared y hat of s minus y prime of 0 minus sy of 0. So this is y double prime. Laplace transform has linearity. So if I know the Laplace transform of y prime, but I want minus 5y prime, I could just multiply that by minus 5. So I have minus 5 times the Laplace transform of y prime, which from over there is, that's a 5, s y hat of s minus y of 0. And then I have plus 6, and just have y hat of s and that this is y prime. Or to be more precise, this is the Laplace transform of y double prime, and over here, y prime. Okay. Next thing I can do is, if I have initial conditions, which I do in this case, I can just fill in those values now, and then I don't have to think about the initial conditions ever again. So I have s squared y hat of s minus y prime of 0, minus 1. So minus of minus 1. Minus y of 0 is 2, so I have a 2s. And then I have minus 5s y hat of s plus 5 times y of 0, which is 2. Okay.
That's an S, right? 5S.
This is an S, yeah. Yeah, I probably should have chosen 5 from respect, but I'll try to make them distinguishable. Okay. Now what I want to do is I want to group all the terms involving y hat of s together. And then everything else that doesn't involve y hat of s, I want to move to the other side. So I have s squared y hat of s minus 5s y of s plus 6 y hat of s on the left side, and then everything else moves to the right side. So I'm going to have 2s is moving over, and then I have plus 11, so minus 11. Okay, yeah. All right. What I do now is I want to solve for y hat of s, because I'm trying to find y of t. So what I'll do is instead find y hat of s, and then I can do an inverse transform to get y of t.
Does that 25?
Oh, that's an s. Okay, so, all right, so I'll try to make my 5s super distinguishable from s's, even have to make them look outrageous. Okay. Now, on the left side, I'm going to factor out a y hat of s. And what's left? I have s squared minus 5s plus 6. And still same stuff on the right side. Now, it's no accident that what you see here is what you would see in your characteristic equation for this problem if you're working out the old way. Just with an s instead of like an r or a lambda. And now I just divide. So we get 2s minus 11 over all this. So now I have at least a Laplace transform of my solution. I just need to invert this Laplace transform to get a solution y of t. But the problem is at this point, it's not written in a convenient form where I can just go to my table, like the one in a textbook, or you might look up online, and just look for the right rule that matches what you have here. You have to rewrite it to get into that form. And so what I'm going to do first is the denominator can be factored. So that would be s minus 2, s minus 3. And what I need to do next is, because ideally, the rule that I would like to use in reverse is this one. Because if I have something like this, the inverse transform of that is an exponential. And exponentials are what we'd expect to have a solution of this anyway, because you can tell by factoring there are real roots. But to get it in that form, can anyone tell me, because you've seen this before in number class, how can I write this in terms of fractions like over there, like 1 over s minus a, something like that? What technique are you supposed to use? Good old partial fractions. I'm sure that brings back some fond memories. So I have to express 2s minus 11 over s minus 2, s minus 3 as a sum, a constant over s minus 2 plus another constant over s minus 3. Now, before we actually, we'll see, I'm doing it on time. Not so great. Now, at least this is the simplest form of case of partial fractions because you have distinct linear factors. All right, so you multiply through by the denominator, and you get a s minus 3 plus b s minus 2. And to get a and b, you use what is called the method of creating zeros. You set s equal to 2 first, and you get minus 7 on the left side, and then this term's going to go away, and you're left with, you're left with that. So a turns out to be 1/7. And then you set s equal to 3, and you get minus 5 over here. And then you have this term goes away when s equals 3, and you get b times 1, so you get b is equal to minus 1/5. So now what you can say is the Laplace transform of your solution can now be written as 1/7 over s minus 2 plus minus 1/5 over s minus 3. And now you can conclude by saying that y of t is the inverse Laplace transform of y hat of s. And the inverse Laplace transform is linear, so you can say that it's 1/7.
Isn't A supposed to be 7?
Hold on. Okay, it's Monday, cut me some slack. So accustomed to these being fractions, I'm not used to a case where it doesn't. Thanks for eventually catching it. Okay, so it's 7 times the Laplace inverse transform of 1 over s minus 2. The whole time I'm thinking, how in the world are we getting this satisfy the initial conditions of these? That's not going to happen. It's like, oh, that's why. Okay, minus 5 inverse transform of 1 over s minus 3. So now what you can do is just reverse the rule that I gave earlier, that the Laplace transform of e to the at is 1 over s minus a, that we saw earlier. Therefore, the inverse transform of 1 over s minus a is e to the at. So it goes both ways. So finally what you have is 7 e to the 2t, just the inverse transform of this, minus 5 e to the 3t. And you're done. You have your solution to your initial value problem that satisfies the initial conditions. Sorry, what? Okay. All right. And actually, you can check by plugging in t equals 0, and then also differentiating and plugging in t equals 0, but that actually does satisfy the initial conditions. Okay. So questions about this process? Okay. So what will happen is, so this is how it works in general. Use the rules for transforming derivatives. All right, 1 minute, I'm going to use it. So use the rules for transforming derivatives, including your initial conditions, to get this algebraic equation. Solve that algebraic equation for the transform of your solution. Then use partial fractions. Now this case worked out nicely because you have distinct linear factors, but you might have like repeated linear factors, or you might have irreducible quadratic factors that lead to sines and cosines. And you'll see, I'll show you more examples of that on Wednesday. And so after you do partial fractions, to get the Laplace transform of your solution in the right form, where you can use those rules, then apply those rules in reverse to get your solution. So we're just going to keep going with that process on Wednesday.